agreement with the AutoCAD, right? I don't know what this is precisely doing, but it seems to give very different numbers.
Yeah.
Is this? I don't know if you have time to discuss offline, but
So Sunja,
Uh-huh.
so you think that you have a kind of weird, is the reason why you had a kind of weird result is that your your supercell was too small.
I
So,
think that supercell is the number of supercell structures are small, I think.
okay.
I only because this structure is very complex, I think maybe we need to generate more supercell structures to fit for the force constants. Here I only generate 50 use the Monte Carlo like random displacement method to generate 50 structures then to fit for their force constant. Because in these first principles calculations, I think the computation is heavy, so I only generate 50 structures. But I also tried the universal potential to calculate force. I generated 100 structures, supercell structures, to fit for the IFC. So this is a different.
But Sunjay, so I
Mhm.
think I want to remind you that we are not so much interested in the universal potential at this point.
Yeah. Last time you say that, then I tried the first principles calculation.
I know. And
Yeah.
then so 50, how many structures do you calculate, Masato, in orthokappa generally?
I'm not sure, but I decide the number of structures to calculate force constants based on the number of parameters. So yeah, I decide the ratio.
Do you know, Jason, specifically for this PRTE, how many structures AutoCappa calculated? Jason?
Oh, I'm not. I haven't checked that for the auto kappa.
Okay. I think
Yeah.
that's a good start. I mean, you should probably know more about what AutoCappa calculation was, and if the number of samples you're taking is much less than what AutoCappa took, of course, then I would imagine easily how things can go wrong. And
Yeah.
also, do you do lasso on this?
Yeah. We in our code, yes, that's we are using the lasso to fit for the force constant.
I see. I see.
Yeah.
All right. So if Masato, if you can answer, if you can pull out the numbers quickly, of course it will be useful. But otherwise, maybe you guys can talk offline a little more, uh,
Sure.
because
Yeah.
at this point, just because of the ratio, I would rather looking at the numbers intuitively and physically, I would rather believe AutoCAPA results than the validation calculation at this point. But you guys can discuss. Maybe there are more. You can discuss more detailed information about these calculations, like the force constants, value of force constants, cubic force constants, and things like that.
Yes.
Right. Okay. Thank you.
Okay.
So anyway, we think in any case the three materials are interesting to look at from DFT calculation perspective, and I think Kedar was writing a note saying we should discuss the experimental part, especially see how the experimentalists are doing. And sorry, I don't know who are the experimentalists in this group. No
I
one.
cannot. It's Christine.
Yeah.
Yes.
You want to share?
First thing,
Yeah,
and
sure.
Jayan.
Right, Christine.
Christine and Jayanta can share some results.
Give me a moment, please.
Sure.
So we synthesize K2SNT5 and I will share the XRD data. So bottom is the S synthesized is the precursor of the K2SNT5, and we synthesize 550 Celsius and at 800 degrees. And as you can see from the phase matching, we got tellurium and tin for tellurium is red, and tin for the gray part. And my question is, how do we know whether we synthesized the right material? Because when I look at the generated XRD from the from Giant, do you remember which website? Oh, when we see the generated XRD graph from the materials project, it seems like it kind of deviates the pattern, and we don't have the CIF files, so I don't know how to verify the results at the moment.
Do you have Christine, do you have the materials project XRD spectra somewhere? You said it's a little bit shifted from that. How bad it, or how much is it?
Let me get the XRD from the
But Christine, while you're finding it, from the XRD and from the Ride-Well refinement, did you get the same space group as the one by Materials Project?
I mean from the XRD, I'm not sure how to find the same space group. How do you usually do it?
From the Ride-Well refinement, you should know the Mycroft letters or sites, as well as the space group, right? From the Ride-Well refinement.
Oh, okay. I'll try with that.
I'm not sure. I am not sure. It's a long time since I did Ride-Well refinement, but maybe June knows this.
Yeah. Space group. So what are you saying? You're saying that, okay, how do you identify space group from the XRD spectrum?
Yeah.
Okay. Yeah, I mean, I would do, yeah. I mean, I think we usually do the other way around and try to get the probably what you're saying, compare the XRD simulation result, and then of course, so we need a CIF file for this. But so what do you think, Martin? So doing this without the CIF file?
You will use the zip file for the refinement, or
But the database doesn't have the C files.
Why?
yeah, okay.
Yeah.
That we can give to you if you use the symmetry operations, the SPG lib. That we could give to you.
Oh,
Giant, do you have any comments?
yeah, I have some comments here. So so the XR result typically require we yeah, there's so many refinement methods, right? So the typical way is, I don't know how to spell the name, but it's Retafield refinement. So that's one way. But any of the refinement will need some expert. So will require a lot of feeding. And the quality of the XRD data gonna be, yeah, you will need a relatively high XRD data, then you can fit the refine the data and get without the previous any zip file from the database, and you will get a new zip. Oh, you also can get some goodness of feed. But I think maybe Haiwan would know how to do this reader field refinement. But prior to that, you can maybe search somewhere or seek help from Haiwan that you can use you cannot directly compare the zip file or the structure from mature project, because typically the lattice parameter will deviate from the experimental one. So you will see some peak shift, and that may lead to some deviation. And I learned something from Pepe. He was doing some like you can use a current zip file from, for example, from mature project. You already know the space group, and there's some software, but I don't know because I'm not experimenting. But there's some software that you can input a zip file and compare, and there will be some doing iteration feeding, and then you can get the how much how where the match between the two. There are two ways, so you can refine and get the shift corresponding to the XRD there from scratch. But this I learned from like Haiwan. He said we would need some experts. And another way is you just need to input it like from mature project that you already had the MPID, right? So you can get the SIF, and there will be some software that can help you to fit how well they fit together. So it's not directly that you compare the XRD pattern directly. It's not
Okay.
the best way to compare whether you synthesize the materials we want. Yeah.
Yeah. But I think you're right. I mean, you don't expect it to have a very good quantitative fit, but at the same time, it's always good to compare what you see in the materials project, and then, if it's completely different or if it's
Yeah,
just
yeah.
a little bit of a shift, right? So,
Mm.
did you find anything, Christine?
Yeah.
Materials project?
Okay. Yeah, I got this pattern from the materials project, and
Mhm.
if we try to fit, there is a peak at like 25, 20, 28, and we are quite matching, and 30, there's no peaks, and for 40, we have some, and it matches a bit, but for experimental, I don't know whether we should form SNTE rather than just TE peaks and SM peaks. I think I can maybe check with Taiwan as well for this.
Yeah, Christian, you can check with Haiwan or Chengguang. Chengguang, I think Chengguang, because he's also doing some synthesize some materials terrarium, right? The TE. So, but I'm not sure. So I cannot help you to explain. Maybe there's some just impurity DE in the powder. So yeah.
Okay.
But it seems currently, from my point of view, yeah, there really some matching. The major peak, we will need to check the major peak. For example, yeah, we need to check this structure has, for example, 100 or 110 or 101, those major peak, if they match, we may have some confidence. So,
Okay,
but we
I
we
will
need
I
some
will check with Taiwan.
I think Jayanta has tried something. He's trying to speak, but his mic is kind of off. He said the XR, he tried the matching between the SIF and XRD, I guess, and then it didn't match. That means the one synthesized is something else. And he's trying to change the precursors and try some other experiments, right? Yeah, I think he did it.
Okay, so direct match may not perfect. So I don't know. Yeah, so maybe we probably need, because this material is not synthesized from the paper, right? Or it's not reported. So probably the
Yeah,
refinement is the best way.
Okay.
I see. This was not. So I remember there were three materials, and one was, I think, the structure itself was reported, but the property was not, and then the rest of two were not reported at all. So the one that you showed us, Christine, this is the one which has never been reported before.
This is reported but doesn't have the experiment, like the thermal conductivity.
Right. So the structure has been reported, but the properties were not reported yet.
Yes.
Okay.
Okay.
So do they have the reported, I guess this is experimentally reported. If you pull out the paper, do they have XRD?
They don't have the experimental patterns, like for example XRD in the ICSD database. We have a similar structure like K2SM4TE6 or something, but doesn't have the K2SNT5, the exact experimental data.
So when you say the structure has been reported, this means that this has been reported experimentally before.
But on the paper, I couldn't find it in the database as well.
Okay. So what am I missing here? So
But it's reported in the ICST, right?
It wasn't on the ICSD.
Okay. Okay.
So
So I see.
I'm very confused.
I see.
so it wasn't on ICSD, but then we flagged it as something that has been reported already.
Yeah, so in reality, what they did was they found the compounds which was not an ISSD, but which the filtering tool by Danny found to be most likely to be low thermal conductivity, the most stable, being likely to be synthesized, and then they took that particular value structure and tried to synthesize it.
Okay.
Yeah,
One
I
of the
mean,
three. It's one of the three. Yeah.
I mean, what Danny did is, I think, yeah,
I'll show
maybe,
you.
yeah, the most possible is just there only like few paper reported the chemical formula. So because
Yeah.
they use the LM based methods to match whether these materials has been reported or not, but
Yeah.
probably they didn't have report any XRD result.
No, they don't have. So we need to generate it ourselves from the atomic structure. But basically, he did this here, June. He took the whole AutoCAPA dataset, passed it through this filter here, and then he shortlisted like 10 compounds, from which he said these three is the most interesting one. And then they had a meeting where I guess Christine was part of this meeting, where they said that this compound might be the easiest one to synthesize. So it's never been synthesized before, but it's reported in Materials Project, and then AutoCAPA found it to be low in thermal conductivity. Yeah, so that's how they determined this material. So we do have the Materials Project structure, and we could symmetrize it so we can get the XRD
Got it.
pattern. Yeah.
So among the three structures that you guys are trying to synthesize, there is no structure that has been confirmed experimentally with XRD before. Am I right?
No, that I agree on.
Okay.
You can see, I think I
Right.
have them over here. Yeah, I can show. Yeah, it doesn't matter, but yeah.
Okay. All right. Now I
So-
see how difficult it is.
So they're completely new material. So now they want to compare and see if
Wow.
it is slow in conductivity, if the autoclave actually did great.
Right. Okay. This is a big deal. Interesting.
Yeah.
This is interesting, but I guess, yeah, I understand this is very difficult. You kind of go back and forth. You take XRD and then you try to match it with a theoretical value for a given crystal structure. And then if it doesn't work, you go back to your experiment, changing the experimental condition a little bit and try that again. All right. I'm starting to appreciate this. Yes. I hope it will work out.
And that's why at some point we need to look at this phase stability and see if there's any disorder or how it looks like.
Right. And this is powder diffraction, right? This is XRD. Yes. Okay. Thank you. So you guys started with this K4SN2 T10, and then this will be tried in serial. So the other materials will wait, and you're going to focus on one material first. Am I right?
I think so. Yeah.
I think so. Okay. Okay.
You can see I found I think I found the list. Wait, please say if it's the correct list. I'm very sure it is, but this list here, this is
Yes.
the list.
I have checked this KS and T10 is not
Yeah,
is
this-
in the
this-
not made position.
Yeah, they found this one. Yeah,
Mm.
you can see all of them here, as I can show you. June. None of them has ICSD IDs,
I see.
meaning they are found to be. But we do know, Christine. We do know, as you can see here, we do know the space group number and other
Okay.
things. So we can give it. So yeah, this is the one which they found to be most interesting to look at. Also because it is the lowest in thermal conductivity.
Right.
And I'm actually quite happy that it was synthesized because it had the synthesis score of, where was it? It was there just before. In here, it was not that high of a synthesis score, 0.56. So that means that it's good we didn't set our threshold higher. So that's a good thing.
And what does the person mean?
That I need to ask Danny about. I think he's the one who will try to make it.
Delwyn.
Yeah.
Who is Delwyn?
No
Gavin
clue.
is a research engineer in Kidas Lab. Yeah, he's
Okay.
helping to doing research under the synthesized material, handling the instrument.
Yeah.
But
Okay.
I don't think he will join the meeting today.
Okay. All right. So no way you're saying, yeah, okay. Refinement, yeah. Fitting the XRD into a similar existence structure. Yeah, sure. Great. So from our side, we just cross our fingers and pray that he will get the structure. All right. Thanks. Thanks for sharing. Pretty interesting. So anything else we are planning to discuss, Norway or Martin or
Yeah, I have updates. I don't know, Raymond, do you have updates today? I don't know if Raymond is.
You can go ahead.
Okay, then I will. I don't have a lot of updates, but I can of course share what I have, and I actually also have a discussion I would like to do. Maybe we actually need June to set up a meeting this week to discuss in details. Let me see here. I'll just do the. Let's see. Yes, much better. Yes, so this is just an update on the local flexibility and the ML tools for predicting lattice thermal conductivity. And before going to our forward model, as we have talked now, I don't know why you said you were not happy to have this universal machine learning potential, June, but
No.
in reality,
I meant on the check-in process, right? So our validation, our task was to validate with DFT calculation. This was what I said. Yes, yeah.
Okay.
Generally, it's okay.
Yeah, because in reality, we would like to train a machine learning potential. I'm thinking about doing with active learning, and I will explain in a moment why. But one can also, as I know you guys are doing fine tuning with the AutoCappa datasets, and try to like use the information already from the universal machine learning potentials to like make it more stable for our phase space, and in reality also make the training faster. Yeah, and there's two ways of doing the fine tuning, both the naive fine tuning, which is transfer learning, where you basically just take the machine learning potential, train your data directly on that model. It's very good. It speeds up it quite a lot. Or I can also do the multi-head, where in reality you use the information from the trained data on the universal force field model together with the data set you have in hand. So in this case, AutoCappa, to do the machine learning model more general, so generalize it in reality. But this is maybe, June, we should have a meeting ourselves, because in reality, I'm mostly interested in trying to use active learning to train our machine learning potentials. And the reason why, maybe I will skip wait for this. The reason why is that when I have trained my model through this package called Curator, which I'm a co-developer on, then in reality, what we can do is we can do uncertainty quantification, which is basically I take all the AutoCappa dataset and then I generate some new data. So in reality, one could take genome, I could run the whole genome, and then I could look at the whole genome and tell you, this is the structures which I believe the data, our dataset needs to improve more, to be more universal. It's basically saying which one is the most out of distribution. And I think that could be very interesting to have a look. So in reality, we do some more DFT calculation, as you said you were interested in, but more oriented towards the out of distribution data. So we cover more phase space in reality. Maybe we should have a meeting ourselves on this, but in reality, I also discussed this with Shuya. And Norway actually, there is a lot of data. That's a good thing, because in reality, we can take everything you guys have done, all the DFT calculation, everything, take all that and train our machine learning force fields. But that, as I think it was Masato who said, that's around 2 million data points. And that's a lot when you think about the materials project data, which they use in Maze, Maze, MP, and Charts, and all these were only 1,057 thousand structures. So maybe we should have a separate meeting, but maybe we should be clever about with what structures we pick and what in reality what what structures to pick in this process, in AutoCappa process here. But maybe we should have a separate meeting about this and discuss. I don't know if Masa is here, if you have thought about something. But yeah.
Masa's not here today, but Masato is here. So have you guys discussed something along this line, Masato, Ju?
Masato discussed very quickly, but not in details. Maybe we should discuss in details.
I have a question about the active learning. Is that for? I mean, the machine learning potentials active learning is for specific materials to fine tune the model, or like the universal potentials use a lot of materials?
No, in reality, the guy who's the main developer is considering trying to do more fine-tuning method into this model, but this model is more you train a machine learning interatomic potential from scratch using the data we already have. Then you do a simulation. In this case, I could do relaxation of all, or in reality, AutoCAPA on all genome dataset, and then it will tell me what structures from this whole simulation, all the machine learning generated structures, which of these structures are the most relevant to do DFT calculations on. That's basically what it does. So it's just a way to basically determine if things are, which material is more relevant to consider than others, compared to the phase space you already have.
Okay, and then operate the DFT to calculate the accuracy result.
Yeah, so basically you can see here in the naive, maybe we should not consider this, but the batch mode we have in reality is that you take the phase space you have here, then you create some cluster points, which is the red dots, and then in reality you compare these cluster points to all the other points, and then you see which one is the furthest away in the Latin space, and then you determine that is the most likely to we need to know more about because it's more out of distribution than the others. It's not clustered towards any known information.
Yeah, so this is fine. So this, so you're basically thinking about including this in the AutoCAPA loop.
Reality, that's why I need to discuss it. In reality, the simulation here should be the AutoCAPA. The one stage you built in reality.
Right. And then you look at the latent space and then try to pick a point where we should do DFT calculation in order to improve the accuracy of the model at the best.
That was the goal in reality, yes.
Right.
To
and then
improve
the objective here.
MLP more.
What do you use for the? So this is for the machine learning model and not specifically for thermal conductivity, I guess. So you want to basically do the force prediction, right? Yeah.
In reality, I agree. I've also thinking about this quite a lot, how to do it the best. But this is for force and calculation reality is. So that's what we are trying to focus on.
Yeah.
So that's why if we do the whole loop here, then what it will do, let's just take one material, right? Then in reality, if I take the calcium telluride we looked at before, then I will do the whole AutoCAPA. And then I will get, I will generate structures from all these procedures here in AutoCAPA loop. I don't know how many there will be, maybe around 1,000 structures will be generated just for one material. I think that's likely. And then in reality, the model here will tell out of these 1,000 structures, which one is the most out of distribution, which one does the machine learning model know the least about and want to know more. And then you do DFT single shot on those materials.
Yeah, this is interesting. So I'm also interested in how, because these are, you said 2 million, but these are fairly small displacement, 2 million.
Exactly. So we need to be clever, because if there's very small displacement, the small displacements are important, but maybe a lot of similar small displacements are too redundant. Yeah.
So Masato, when you do these force displacement calculation, but at least you have taken symmetry into account, right? So in terms of redundancy, we're not really double counting this exactly the same configuration, considering the symmetry. These are all sort of independent in terms of the symmetry, right?
Yes.
Yeah, but then the displacements are typically pretty small. What do you do? So when you do random displacement with lasso, do you fix the magnitude of the displacement, or do you give the maximum displacement?
I fixed the magnitude of the displacement.
So the magnitude of the displacement is always fixed, and maybe I'm just guessing, but it's fixed for harmonic, and that you have another displacement for cubic.
Yes.
And this is like 0.01 and 0.03 or something.
Yes.
Okay. All right. So yeah, it'll be interesting. Of course, Martin, we can always do other calculations because these calculations were basically done not to train the machine learning model, but it was actually to get the force constants. But in theory, yeah, one can do additional calculations. I guess what I'm saying is,
maybe it's not necessary. Then it was just a thought. Maybe it's not necessary to do these extra calculations.
Okay, but anyway,
Could be.
first you can do the training and see what the accuracy of the trained model is, right? So
Yeah, so we need to find a good database to train machine learning model on anyway. So I think it could be a good idea to discuss. Yeah.
Good. All right. So Masato, maybe this is an interesting topic to discuss further, including Masa,
Yeah.
and
think
maybe
so.
what you guys want to schedule a meeting. And if I can make it, I'll be very happy to join, of course. But you don't have to wait for me because
Okay.
I don't want to delay things.
Mhm. Okay.
Do we have anything to report to people about what Masa and Jay, you guys are doing, or about the machine learning side? Or maybe we take it next time.
Yeah. I have a small comment. I just heard from Masa, and yeah, using our data from our database, Masa is trying to do basically same thing for the initial part. And he was saying that because our database contains supercell structures, like I think the maximum number of atoms is 200 atoms. And in this case, memory is problem will be the problem. And yeah. I just heard about this.
That is true. When maybe I should talk to him. I maybe have a solution. We can try some of the GPUs I have. Yeah.
I see. Okay. Yeah, please talk with Masa.
That is an issue. The large supercells is going to be an issue. It's not a bad thing. It's a very good thing we have supercells because many people does not have it.
Yeah.
They assume periodic boundary conditions. So it's a good thing we have supercells, but we need to the memory is the issue.
Okay, I see.
Yeah, cool. Maybe let's schedule a meeting and then let's discuss.
Yeah.
And anybody from Singapore who would like to join, write to me, then I will join you in the loop. Cool. Then quickly moving on to what I showed you before. Now, I don't think maybe I should go into this in more details, but we are also building the thermoelectric materials funnel, where in reality, we want, based on the lattice thermoconductivity, the energy hall, try to narrow down from a big data set. In reality, all the things which Raymond will generate for us, we will determine which one we think will be the better. Maybe it's not necessary to do all these things because I think Raymond and Shuya are looking at conditional search. So maybe this will not be necessary, but if you want to do random search, this could be interesting. Yeah. And we want to include some more things, maybe find out when to do the DFT optimization because we know that the machine learning is not as accurate. Nongwei have shown this, but we would like to do as least DFT as possible. So we need to talk when to do the DFT. And then maybe we should also have what me and Shuya looked at last time, the site disorder probability included in this loop as well. Yeah, so we're looking at this funnel and working together with Raymond to make it happen. So we can generate a shortlisted like the ones the experimentalists are considering at the moment. And then for that, we need to predict the lattice thermal conductivity. This is very crucial. And as I mentioned last time, we would like to take the AutoCappa dataset. We want to take a machine learning predictor and then predict the lattice thermal conductivity. And for that, we are doing this AutoCappa competition. And now the deadline has been shifted from the 18th to the 29th of October. And we will find the best machine learning predictor on 3 data splits. The 3 data splits are the random split, the space group split, and the group split. In reality, it's very important that you train this log K-lattice. This is the one which we will evaluate on. But this is the three splits we are considering in this competition. And a trap which I will like you to mention is that be careful what structures you choose, because the structures, which is called structures, are the ones from a serious project, and they are actually pre-relaxed with machine learning. If we use code like diffCSP, now Raymond, please and Surya, please correct me if I'm wrong. But if you use diffCSP, it's totally fine to use that particular structure as the input. But if you use Y-form, which Raymond and Surya is considering, then you need to use the symmetry structure instead of the structures, which is already relaxed by DFT. Or else you need to do a machine learning potential to relax the structure. And then remember, you can use the information from the machine learning potential for that as well. I don't know, Raymond, you agree? Or
Yeah, I think that's fine. Like the symmetrized structure, I guess give you a additional step for pre-processing, like processing after the generative model, so that you make sure for the models that generate based on space group labels, you make sure that the generated one is the same as the generated structure has the same characteristics as what you inputted there, right? That's
Exactly.
important.
Yeah. So what I'm saying is maybe JU, I don't know which one you used, but try to use the symmetrized structure. It's also fine to use the structures, but then remember we need to do a machine learning relaxation from Y-former if we do that. Yeah, it's just a trap to be careful about in this model. And then models are already in. And again, if you have any question about this competition, write to me or Danny, then we will help you. And models are already in. And in reality, we have 4 models already. We have CGCNN, which is the baseline for June. And those who doesn't know, it's one of the most easiest ones to do. That's why we call it the baseline. And Danny has also, so for the people in Singapore who doesn't do it, Danny is also looking at Roost and CrabNet. He didn't write it, but he's trying to do that. And we'll also add them as the baseline. And then we have tried people have tried the different models. But at the moment, it looks like Jeyu is the one who wins with his LEGNN model.
I need to clarify is that because I'm not I didn't use I for each split data set I optimized the parameters, so there are maybe some mistake for the training.
Okay.
No,
Actually,
no worries.
No. We need to standardize the training config.